we have the momentum principle. The momentum principle says that if I know the net force on some object, I can find its rate of change momentum. So if it's constant, I can write this as a finite difference, or I could take the limit as delta t goes 0 and get it as a derivative, and that's fine. And so we have used this to say, like, if I have the net force and the momentum is mass and velocity. If I have the net force acting on some object, then over some short time interval, if I know the initial momentum, I could find the final momentum. And that's all fine and dandy. But what if I want to go the other way? What if instead of, looking at this principle, let's write it like this: F net equals the derivative of the momentum. What if I want to know, if I know something about the change in momentum and I want to find something about the force? That's a little bit more difficult. Really what we want to do is the following. Here's where we're going to go. So imagine that I have some object following some path like this. And so I know that the momentum is this way. That's the momentum. And so I want to know, based on the way the momentum's changing, it could be going faster, it could be increasing in speed, increasing in magnitude momentum, or it could be changing direction. And I want to break those into two different parts. So to do this, what we're going to do is to use a trick. So I'm going to derive this idea, and we're going to condense this into circular motion. And I'm going to show you an example in Python that I made that I think is kind of useful, but maybe it's not completely useful. So I want to take the derivative of this and write it as an expression. But to do that, I need to write the momentum. I'm actually going to write the momentum as momentum is the magnitude of the momentum times a unit vector in the direction of momentum. And so we could also just write this as p hat. So any vector you can write as its magnitude times a unit vector because of the definition of unit vectors. Remember, we define a unit vector p hat as the vector p divided by the magnitude of p. And so then if I had to solve for p, that's all I have to do. That's how I get that. But now in this form, I can actually take the derivative. So let's take the derivative of p with respect to t. That's going to be the derivative of, I have a product now, right? And both of these can change. So I'm going to take the derivative of this first one. So I'm going to say the derivative of the momentum with respect to time times p hat. But now I have to take momentum times the derivative of the p hat vector. So I'm going to say plus p times d p hat dt. And this is really useful because now I can say this is equal to, this is in the direction of the momentum. So we're going to call this F parallel. So the change in momentum due to the change in magnitude is going to be F parallel. It's going to be the force in the direction of momentum. And we're going to call this F perpendicular. And that's the change in momentum because the thing changes direction. So let's imagine that we only have an object changing direction. And so that would be, and a great example of that would be something moving in a circle. So here I have an object moving in a circle of radius r. So here at some time, it's going this way. I'm going to call that just p hat. I only care about p hat. I don't care about p. And then a little bit later, it's over here. We'll call it p1 hat, p2 hat. They're in different directions, so they're different unit vectors. And during this time, it goes from there to there, and that angle is theta. And it's a short time, but I'm drawing it as a big angle, and that's fine. So if I just draw this triangle right here, I get this, that, theta, r. So the arc length right here, I know there's a relationship between theta and the arc length, right? I can find theta as the arc length divided by r, and that will give me theta, right? Yeah, r theta is this. Yeah. So I can, and now how long is this? Well, let's write this as v delta t, because if it's moving with some speed v over some time interval delta t, don't really care what it is right now, then that's how far it's going to go. It's going to go the distance of v delta t. So I can say theta is equal to v delta t over r. And that's fine. Now, let's look at the unit vectors right here. I have P1, I'm going to draw them big. Here's P1 hat, and then I have P2 hat, like this. And they both have a magnitude of 1, and then this from here to there would be delta P hat. And this angle is also theta, right? If I move this down here, you can do a little geometry and see that that angle is the same as that angle. So now I can write delta P hat is going to be equal to P2 minus P1, which I don't really care about that. What I care about is this angle theta. If I do the same trick, I can say this is kind of like, if theta is small, this delta P is like an arc length. And this has a magnitude 1, so theta is going to be delta P hat divided by 1, because the magnitude of this is 1. And we're dealing with magnitudes here. But the first thing you see right here is the direction of delta P is that way. So if I'm going from here to there, delta P is that way. So right away, I get a object changing momentum moving in a circle. The change in momentum is towards the center of the circle. That's going to be very important later. But now I have theta is delta P hat. I can set this equal to this theta. They have to be the same thetas. So I have delta P hat equals V delta T over R. And now if I divide both sides by delta T, I get delta P hat over delta T equals V over R. And so this is the magnitude of dP hat dt, V over R. Now I can go back and look at that F parallel, F perpendicular, I said was P times, and this is the magnitude, P times dP hat dt. So that's just going to be P times V over R. If I write P as mv, this is going to be mv squared over R. And this is really important. We call this centripetal force. It is literally center pointing force. This is the force that points in a circle because it's the change in momentum towards the center of a circle. Okay. Now, there's two things that are important. This is the magnitude of that change in momentum towards the center of a circle for changing direction, and the direction is towards the center of the circle. Okay, let me show you an example in Python, and then I'm going to draw it. So I made some code, and that we can look at just for fun. So this is, I'll make it a little bit bigger. And the code really isn't important. I mean, it's not super great, but it's fine. And I'm going to run, so there's a mass swinging on a string. And the cyan arrow is gravity. The yellow arrow is the tension. And the red arrow is the total force. Let me run that again. And now I'm going to draw this diagram at two different points. This is actually, I'm not going at, I need to go at 90 degrees. Let's change this to 90 degrees. I did 85. I don't even know why I did 85, but 90 degrees. So it starts off, there's no tension, right? There's no tension when it starts off. And at the bottom, the important thing is that the force is the tension straight up, the gravity straight down. So let's draw those two instances to talk about, I didn't switch. To talk about perpendicular and parallel forces. So here is my pendulum. And if I'm right here, I have the gravitational force is pulling down. I'll write that as mg. And there is no tension, so the net force is down. So that's F net. Now, this is constrained to move in a circle. So it can't move straight down. Actually, this would be tangent to the circle. But right now it's not moving at all. So there's no change in direction. So I would have right here, F parallel is mg. And so what that means, that's the magnitude. This gravitational force is going to change the magnitude. So this changes the magnitude of P. because it's in the same direction. And so what that means is it's going to speed up. So when I let this go from rest, the only force is it's not going to change directions because it's not going in that direction. It's just going to increase the magnitude of the momentum, and that's what that does. Now, once it gets down here to the bottom, gravity is still pulling down, mg. The tension is pulling up. I'm going to draw it bigger. But the most important thing is F net is completely up. Call that F net. And the momentum is this way. So now you'll notice that this is a perpendicular force. It does not change the magnitude of the momentum. It only changes the direction. So this is going to be equal to PV over R, or mv squared over R, same thing. And this is the magnitude. That has to be true, right? So it does matter about the radius of the circle it's moving in, the velocity it's moving down here, and the momentum, which has mass and velocity too. So that tells me something about the net force in this case. So these are the two easy cases. So this one makes it speed up. This one makes it only change in direction. But what if I'm right here? If I'm right here, the net force, the tension's going to be pulling that way, gravity's this way. So I'm actually going to get this. This is my net force. So I have part of that net force is in the direction of the momentum. That's going to cause it to speed up. And part of the force is perpendicular to that, and that's going to make it change directions. And so you may think this is all just BS and it doesn't really matter. And what's the point? And the point is that we can arrange situations. If I have a mass right here, I could find how fast it's going to speed up in a short amount of time by finding the force in the direction of momentum. And I could find the force in the direction of the center of the circle by knowing the radius and the velocity. So it's easy to break those down. Another great example. What if I have the Earth and I have an object orbiting the Earth? This is a tough situation, right? Because the gravitational force pulls that way and is constantly changing direction. If it's in a circular orbit, though, the distance doesn't change, so the magnitude stays the same. So I can actually write F net in the R direction, just for simplicity, is going to be, let me write it over here. F net in the R direction is going to be negative G, mass of the Earth, mass of the satellite, over R squared, and that's going to be equal to P M over R, or M V squared over R, because that's the radius of the thing. And I can use that to solve for the velocity needed to make something move in an orbit. Right? I know that these things have to be true. It's only changing directions, not changing speed. This is a stable circular orbit. So if I do that, this mass cancels, and I multiply both sides by R. Oh, this is negative technically because it's in the negative direction, negative R direction. The negatives cancel, and I get V equals the square root of G ME over R. And that's the velocity I need to be in orbit at a radial distance R. So this is R. Okay, so it is kind of useful in a lot of different situations, especially when we know something about the motion and we want to use the knowledge of the motion, knowledge of the change in momentum to find out something about the forces. In this case, we could find out something about the forces either way. But in the case of a string with tension, we can't find the force. It could be any force. It's a force that makes it stay in a circle, so it's a little bit more difficult. At the end of the day, this is what you need to know. F perpendicular is mv squared over r. And if it's not moving in a circle, this is the radius of the circle it's at that particular time. Matter and interactions calls this a kissing circle, but let me just draw it really quickly. So if I have an object moving like this, like that. If I'm at this point right here, what's the radius? Well, I could draw a circle that matches that and just touches that one point, and the radius of this circle would be r. So r can change in real paths, but we want to deal with situations that are easy enough to deal with, and that is circular motion, centripetal force. The end.